Let's get started. Good morning, ladies and gentlemen. I'm Hiroe Yamazaki from University of Cambridge. And first, I'd like to thank for the organizers of this exciting program. I'm officially staying here in Newton Institute in November to December, but I'm always in Cambridge anyway, so I'd be delighted to talk with you if you would like my talk. And all right, this morning, I'd like to introduce my Castle model, which is developed for high-resolution atmospheric simulations over mountainous areas. I've been developing this model for 6 years and just got a PhD half a year ago in Kyoto. And now I'm as a postdoc in the University of Cambridge. I'm continuing this work for 2 more years. And here the background picture is a map of topography around my home university, Kyoto in Japan. Kyoto is the most traditional place of Japan. We have a lot of temples, terrain, some castles, and also famous for the old imperial palace, where Japanese emperor lived for over 1,000 years. And with respect to the topography, the center of the Kyoto city is pretty flat, but it's surrounded by mountains, and we can see steep hills and complex topography along the hills. Generally speaking, the model topography gets more complex and steeper with the increase of resolution. That's why a more precise representation of topography is important in future high-resolution models. My model named Sayaka. This model aims at such kind of outer high-resolution simulations that use horizontal grid intervals of less than 100 meters for mountainous areas. Okay, here are the current publications of my model for your reference. The name of the model, Sayaka, has no particular meaning, basically. Just a popular Japanese girl's name. This model is currently a regional and dry model with no water vapor. So all of these papers discussed the dynamical core of the model. And the dynamical core is designed to precisely capture the dynamics generated by steep and complex topography. The description of the model is shown here. Sayaka is currently a 2-dimensional model, and the equations are fully compressible. So we use the finite volume method for spatial discretization. The blue-colored figures are characteristic of a model. First, the Castle method in a model uses a cell-merging approach in combination with the original semi-staggered variable arrangement, which I will show you later. In addition to that, a block-structured mesh refinement approach is introduced to obtain very high resolution for boundary layers near the topography with high computational efficiency. Now I'm going to explain the details of these characteristics of a model. So again, first, the most distinctive feature of my model is the use of castles as a representation of topography. As you know, the current atmospheric models commonly use the terrain flowing coordinates to make it easy to impose the boundary conditions on the terrain surface. And this approach has the advantage for gently sloping topography. However, when the slopes get steeper, it is well known that the terrain flowing models suffer from large truncation errors due to the centroid intersection of grid lines. In particular, inaccurate evaluation of the pressure gradient leads to artificial circulations around steep slopes. Cartesian models, on the other hand, immerse the topography in regular Cartesian grid. And this leads to irregular grids near the boundary. And we use the finite volume method for spatial discretization. Because this method keeps the model levels horizontal, regardless of the steepness of the topography, it doesn't suffer from truncation errors in terrain flowing models. For example, here I performed the two-dimensional comparative simulations of flow over a steep mountain using a terrain flowing model developed by Satomura in 1989 and my Cartesian model. In this test, a semicircular mountain is represented by terrain flowing grids and Cartesian grids, respectively. We can see that in the terrain flowing models, the computational grids are largely distorted along the steep slopes at the foot of the mountain. And here is the result of flow after 60 minutes of integration. The right picture shows the vertical velocity field calculated by the terrain flowing model, and the left picture shows that by the Cartesian model. The velocity field in the Cartesian model is clearly less noisy than that in the terrain flowing model, especially Schrieffer's vertical velocity mode just above the mountain disappear in my Cartesian model. Therefore, this test proves the advantage of Cartesians over the traditional terrain flowing grids for simulating flow over a steep topography. However, at the same time, the immersed boundary in Cartesian model causes some difficulties in atmospheric calculations. And there are three key points in atmospheric Cartesian modeling, in my opinion. The first point is how to avoid severe restrictions on time steps due to the small cut cells. Small cells cut by topography, like this cell, require small time steps to satisfy the CFL condition. And to keep the computational time reasonable for atmospheric simulations, we should find a means to avoid this severe restriction on time steps. There have been a variety of methods to solve this small cell problem, and my model uses a simple cell merging approach. In this approach, small cells cut by topography, which volume is smaller than half of the regular cell, are combined with a neighboring grid. We use both vertical and horizontal combination depending on the slope angles. That is, small cells on the gently sloped mountain are vertically combined, and small cells on steep slopes are combined, each right or left in the fluid. This approach has the advantage of naturally avoiding severe CFL restrictions, maintaining the rigid evaluation of cell volumes near the boundary. It also keeps the model's conservation characteristics. Now, the second point is how to accurately evaluate the pressure gradient near ground.
Can I ask you a question about the last
Yep.
video? So if you in the vertical, if you join the two cells, you only have 1 degree of freedom, right? So you have one temperature or. So
yeah, this pressure point.
Okay.
Is that, yes.
So the momentum equation at the green points, if the system is stratified, how do you stop there being a pressure gradient, a false pressure gradient, because they both see the same density or buoyancy on one side, but different buoyancies on the left-hand side? Yeah, so are you asking about the calculation of velocity, right? Yes, the acceleration is a pressure gradient.
All right, so I will talk about it
okay, right.
for second. Yeah, it's a very good question. The second point, it's most important in my opinion. is how to accurately evaluate the pressure gradient near the boundary, because some velocity cells in custom models may not have pressure points necessary to calculate the pressure gradient. There is a simple example. Consider the case shown here with the standard staggered grid arrangement, U, W, and pressure. In this case, these two pressure points are underground. And this causes a difficulty in calculation of vertical pressure gradient at this W cell, for example, because one of the pressure points associated with it is underground. And also, the calculation of horizontal pressure gradient at some U cells like this is also complicated. And these velocity cells then generally require the evaluation of surface pressure to calculate the pressure gradient, but this may cause a particular problem in atmospheric simulations, because we cannot use zero gradient pressure boundary condition for density stratified flow. So in this study, to avoid this difficulty in pressure gradient computation, I introduced a unique arrangement of variables shown here. Here, the scalar variables are arranged on the cell centers, and the velocity components are arranged on the corners of the cells. And with the immersed boundary, velocity components are arranged directly on the topography, which leads some advantage for calculations near the boundary, because this enables direct evaluation of the velocity on the boundary, thereby simplifying the calculation near the boundary. For example, let's consider the case shown here. In the left picture, relatively gentle slope is represented, and in the right picture, relatively steep slopes are immersed in a grid. And in our method, first, scalar variables are arranged on the cell centers, indicated by circles here. And next, cut cells whose center is underground are merged with a neighboring cell, either vertically or horizontally. And the direction is depending on the slope angles. And finally, velocity components are arranged on the corners of the cells, indicated by squares here. And please note that the velocity points in our method is not underground, but directly on the surface. So now I will explain the calculation of velocity in our model, which is the key feature of our method. The velocity at cells which retain rectangular shapes, indicated by green cells here, this should be calculated in a standard way. On the other hand, the calculation of velocity near the topography, indicated by blue points here, is complicated, as I explained before, because some of the pressure points are underground. So there are several ways to estimate the underground pressure, but I don't want to estimate the underground pressure because there's no meaning on underground pressure, in my opinion. So in our method, we avoid this complexity by calculating the velocity on the boundary first, indicated by red points here, using appropriate boundary conditions. For example, if you use the boundary conditions as a non-slip boundary condition, all boundary velocity here is set to 0. And when the free slip boundary condition is imposed, our boundary velocity calculated from green point velocities surrounding the boundary point, so that the component of the velocity that is tangential to the surface is preserved. For example, in the case shown here, the boundary velocity VA is calculated using the unit normal vector NA, like this. Here, velocity above the normal direction VP is calculated first, and VA is set to the tangential component of the velocity VP to the surface. And there are many ways to obtain a velocity in the normal direction, but at the moment my model uses this simple first order calculation for calculating VP for just a computational simplification. So we can use more higher order accuracy for the estimation of this velocity above the normal direction. And the boundary velocity on the steep slopes are calculated in the same way. And after evaluating the boundary velocities, we calculate the velocities on blue points. And here, the trick is all the blue points are on the merged faces of the cut cells. So here I assume a linear distribution on each merged faces and calculate the blue points using this point, using simple linear calculation. And the velocities on the horizontally merged faces are also calculating in the same way. With this three-step calculation of velocity, by first calculating the velocity at the rectangular shapes, and second calculating the velocity on the topography, and finally calculating velocity on the merged faces, all velocities are obtained without complex estimation of underground or surface pressure. In addition, our model requires no merging forces for velocity cells, so the computational cost of merging cells is reduced. Is it clear for your question? Yes. So we basically avoid pressure gradient calculation near boundary.
Well, just
Yeah.
so it sounds like because you're interpolating for B for the blue points, you've actually reduced the degrees of freedom in some sense.
Yes. So basically,
when you had a merged cell where you got rid of the degree of freedom and the buoyancy, you also did something similar.
Yes.
So there isn't an extra degree of freedom, which is.
So I'm not familiar with the freedom discussion. So that means what's the meaning of
Unknowns, yeah. So
yeah.
You have when you merge a cell, you had two unknowns and you turned it into one. On the velocities next to that, you also got rid of an extra unknown because you used interpolation.
Yes.
So I think that works, yeah.
But that unknown never really existed. I mean, there is only one unknown for that merged cell.
That's my point.
Yeah.
By merging it,
Yeah.
you got rid of an unknown.
Well, got rid of, but it was never really there.
Underground all the way. So
The
velocity one, the blue one, you'd have too many velocity degrees of freedom if you kept it, so you do it dependent on the other two.
I think
You just sort of moved it from the blue point to the red point in a way.
Yeah, that's what my comment was going to be. In a way, one could visualize the method as a staircase with a few triangles and with a modification to adapt to the boundary. So you get just a staircase grid, but you adapt to make it accurate at the boundary.
So eventually, the velocity calculation in my model is more like finite difference because there's no finite volume calculation. I mean, for the say pressure here, I used this combined Cartesian grid and calculated the flux between these cells. But for the velocity, I just calculate the velocity on the rectangular cell, and other velocities are diagnostic calculation. So it's like a combination of sort of staircase for velocities and cut cells for pressure but still all these velocities on the topography are calculated by depending on the angle of the topography and not cut cell calculation, but not the staircase. So in between, I think.
We should move on because we're
All right.
already
Yes.
at the time.
So clearly there are some inaccuracy here. So it is more important to obtain high near ground resolution here, because if I use coarse grid around the boundary, the inaccuracy occurred here could be substantial. So the start point is how to obtain high vertical velocity, high vertical resolution near boundary. It is important for resolve the boundary layers, and also important for put the enough fine resolution near the topography. And high vertical resolution near the boundary is easily obtained in the terrain flowing model by stretching. But in cut cell model, it could be difficult when you have 3,000 meter or 4,000 meter high mountain. And if you want to have 10 meter high resolution near the ground, the simple stretching needs substantial number of levels. So in this case, we need some scheme like this to achieve very high resolution only near the topography. In this study, Sayaka employs a block-structured Cartesian mesh approach in combination with cut cells near the topography. In this block-structured mesh refinement, a flow field is divided into a number of blocks like this, and each block has the same number of cells. In this case, there are 4 different sizes of blocks here, but each block has 8 times 8 cells, regardless of the size of the block. Therefore, the local computational resolution is determined by the size of the block, so that the locally refined grids at arbitrary boundaries can be obtained by refining the size of the block near the boundary. And one of the attractive features of the block structured mesh refinement is that it allows the direct use of existing Cartesian grid code. And moreover, the same number of cells in each block provides an advantage for parallel computing, because the load balance of each block should be equivalent. Now, in applying block structured mesh refinement to atmospheric models, flux matching between different sizes of blocks is imperative to keep the mass conservation. In this study, I proposed a simple flux matching algorithm which is suitable for the block structured Cartesian mesh refinement. And here we use a subcycling time step. So I guarantee that the coarse cell flux, here Fc, equals to the fine cell fluxes accumulated during the subcycling steps using this simple calculation. Though I don't explain it in detail today, this algorithm ensures mass conservation on a refined mesh with a slight runtime overhead. I will demonstrate it numerically quickly from the next slide. Here is a test using a simple diffusion problem. And here the domain consists of 112 blocks with 64 times 64 cells in each block. There's no cut cells in this test, and 0 gradient boundary conditions are imposed on the boundary. And I hit the yellow region first and calculate the diffusion problem. This figure shows the simulated temperature field after 100 hours of integration using the model with and without the flux matching algorithm. Though both results give the smooth conduction of heat, As you can see, the simulated temperature is smaller without flux matching, is smaller than that with flux matching. To make it clear, this shows the time change of the mean temperature normalized by the initial state. It clearly shows that the mean temperature remains constant in the result with flux matching, whereas it decreases less than 85% without flux matching. And this picture shows the speed up ratio to estimate the scalability. Here, OpenMP is used to parallelize the model code, and the parallel efficiency is about 80% with 8 processors. Though the current parallel performance is not super high, but this is the first trial of the model code, and there are some room for performance improvement. And also it shows the introduction of flux matching algorithm doesn't alter the high parallel efficiency of the block-structured Cartesian mesh approach. The final result I show you today demonstrates the performance of the Castle model with a block-structured mesh refinement. In this case, the domain is divided to a lot of blocks this way, and each block has 20 times 20 cells. And a semicircular mountain is located here. And the right picture is the enlarged view of the block, contains the mountain. And minimum resolution is 62.5 meters. And there's a merged capsules represented here. This is the flow result on locally defined mesh. And also, I compared the results to the uniformly defined mesh throughout the domain as a proxy of the exact solution. As you can see, the model successfully reproduced a smooth and accurate mountain wave comparable to the uniform fine-grid computation. And at the same time, the computational time, calculation time, was about 30 minutes with locally defined mesh, while the fine mesh calculation needs 24 hours. Therefore, we conclude that our model Saga makes it possible to simulate flows over steep topography with sufficient accuracy, high near-ground resolution, and also high computational efficiency. Now, let me summarize my talk. Here is the summary of the characteristic of my model, and also some of the remaining problems are shown here. And I'm currently working on upgrading this model to 3 dimensions, and I hope I can show you some 3D results on the PDs on the sphere. That's all, thank you.
Thank you very much. We have time for 1, maybe 2 questions.
I guess sort of the conventional wisdom says that cell merging is hard to do. It's hard to get computationally right, and there's like too many choices, and especially in 3D,
Yes,
it
it's
becomes, most people I know don't even contemplate, but it sounds like you figured out how to do it. So.
I'm now currently doing 3-dimensional cell merging modeling,
Yeah.
and I found it not possible.
Ah.
I could have some results on the conference in 3 weeks, so we can discuss about it in detail.
So it is possible.
It is possible, trust me.
I mean, it'd be interesting to find out just what,
All right. So it's quite important to make the scheme simple because cell merging is generally complex. So that's why I use some simplification near the boundary to make it easier to make it into 3 dimensions. Thank you.
Certainly very impressive, all the different aspects of it that you've gotten put together and made to work. In thinking about this problem, one of the things that I've worried about is where you assume the cell centers are. And we have these cut cells,
Yes.
but you're leaving the the variables defined at the center of the uncut cell.
Yes.
But the actual centers are, say, somewhat higher in the middle of the actual cell. And for like variables like potential temperature, pressure, and so on, there are significant vertical gradients of these quantities. And so as flow is moving across a cell boundary, as it moves along the slope, it's seeing those vertical gradients. And I'm wondering what errors are introduced by leaving those cell centers in the center of the uncut cells.
I'm thinking about the problem for 6 years basically. Because the tricky thing is if I move the cell center for the pressure cell, it's going to be distort the vertical velocity cells. But I'd like to keep it rectangular because if it's going to be distorted, it's not Cartesian grid.
Well, to me that's the sort of the conundrum here is that we like these cut cells because we can do our pressure gradients along horizontal surfaces.
Yeah.
But right along those cut cells, the connection of cell centers is not horizontal anymore.
Yeah. So move the pressure, and it makes the velocity is not on the cell center. So I have to move the velocity second, and I have to move the pressure next. It makes like a spring dynamics in Nikon, but it's not a Cartesian custom modeling anymore. So basically, my strategy is put the very fine resolution in the topography and reduce the effect of the difference between actual cell center and cell center should be, and makes the error, minimize error. It's the current strategy, but I'm thinking about it.
We must move on. Sorry.
Yes.
I think there's lots more discussion to be had here, which hopefully there'll be plenty of time for a coffee afterwards. I'm very pleased to introduce Bob Halberg.